Hi, I'm Ines, and this video presents our work and paper about what we call tap stimulations as an alternative to the vibrations when conveying the apparent haptic motion illusion. The apparent haptic motion is one of the numerous tactile illusions used to enrich devices and transmit messages. This illusion has been studied since 1917 and consists of the asynchronous activation of discrete stimulation points with vibrotactile actuators on the skin in order to convey sensation of continuous motion. Already studied in various body parts, such as the back, the arm, and the hand, studies have also investigated the apparent haptic motion, both in 1D and 2D patterns. The apparent haptic motion represents an interesting tool to indicate directional cues and provide sensation of movement, making it interesting even more for applications such as navigation assistance, which is our main focus. However, transmitting complex vibratory messages or combining multiple vibrotactile signals represent a quite challenging task because of the risk of altering the perception or creating tactile noise, referred to as tactile clutter, especially during prolonged use. Thus, finding an alternative to vibrations for conveying the apparent haptic motion is a research topic of interest. Our work focused on testing and comparing the perception of the apparent motion in vibratory mode versus a continuous stimulation. This continuous mode was induced by a sustained pressure and was called tap stimulation. To investigate the robustness of the illusion and its adaptability to portable and oval-shaped devices, we conducted our experiment on 5 different curvatures. The study was realized with 3 custom-designed electromagnetic actuators fixed onto a flexible 3D printed handrest, which curvature was adjustable. A controller and amplifiers were also used for signal processing. These actuators were used both for vibratory and tap mode. Only the signals sent through the controller were different to convey the 2 sensations. The vibratory mode was generated with a sinusoidal carrier within the ramp envelope, creating the oscillation of the actuator mover, while the tap mode was made of 3 simple ramp signals up to 6.5 volt sent synchronously to the actuators. The experiment was conducted in a dark room with 18 participants wearing noise-canceling headphones. The stimulations were conveyed along the palm and the middle finger. Besides the 2 ways of stimulating, vibratory and tap, we also considered 2 directions of motion, distal and proximal, and 5 different curvatures of the contact surface. After the stimulations, the participants answered questions about what they perceived. First, about the perceived orientation of the movement, distal or proximal. Then, they had to rate the ease to determine this direction, the smoothness of the stimulation, the pleasantness, and the fatigue on their hand, all of those on a 7-point Likert scale. The results showed that whatever the curvature and the signal type, the participants could perfectly sense the direction of the apparent motion. There were also no impact on the ease to determine this direction, the evaluation of the stimulation smoothness, or its pleasantness. Only a light effect of the curvature on the fatigue was found with tap stimulations, which was found to be a probable consequence of the uncomfortable wrist position. At the end, we found that the apparent haptic motion is a robust illusion on curved surfaces. We also found that vibrations are not a mandatory factor to create the apparent haptic motion. Besides, tap stimulations are interesting for prolonged use to convey the apparent motion illusion, and it can also be used to create multimodal devices associated with vibrations, for example.